little bit about margin of error and other things that kind of go along with this. And I'm going to start with this formula. This is something that you should be familiar with. It is, when we talk about standard normal, this is the idea behind using different values or trying to figure out what is or would not be an acceptable value for hypothesis testing based upon a certain value of z or vice versa. We're trying to figure out, well, we have these two things. We have x bar and we have mu, and we're trying to say, I don't know what that is right there, but we're trying to say, what is the difference between these two things? Is it acceptable? What's the value of z that we end up getting out? Now, we don't necessarily have to do this with standard normal. We can have some other value for sigma, which is our standard deviation there, and we can just plug those things in and figure that out. Now, what we have here is the value of n, so we're actually going to say, well, based on a certain population size, what is this value for z? And we can go the other direction with it. We can say there's a value for z, and can we figure out other things? And that's one of the things I was going to look at today. And primarily, we're going to look at what does the value for n have to be for a particular event to occur, right? So let's say we want the margin of error between x bar and mu to be something or less. What does n have to be in order to make that happen? So I just wanted to develop this formula. Now, this isn't necessarily something you're going to have to ever recreate or do on your own, the algebra behind this, but I think it's important for people in general just to see where these values come from. So I'm going to just do a little bit of algebra here. I'm going to kind of roughly go through this. You can pause this and work this out on your own as you need to figure out what I'm doing or to verify what I'm doing as I go. And I'm just going to do that process there, right? So I'm just going to multiply both sides by the denominator. And, well, now I have another fraction here. So I have z times sigma, and that's equal to the square root of n times x bar minus mu. And then I end up with z times sigma over x bar minus mu equals the square root of n, which means that I have z times sigma over x bar minus mu squared equals n, which means that we now have a formula that allows us to be able to connect the population size, which is what n is, right? So this is essentially saying the population size, not population, I'm sorry, the sample size that we need in order to make this work, right? So when we look through this, we're saying I can plug in a value for z. I know a particular confidence interval, right? Let's say that I have a predetermined value of some sort. Like I want alpha to be equal to 0.05, which corresponds with a 95% confidence interval, right? So that'd be z is equal to some value, and we go to the z table and we find that value, right? And one other thing we can do here is we can just go ahead and assume standard normal, right? Which means that our standard deviation is 1. And in that case, then we have this x bar is equal to, x bar minus mu is going to be equal to something, right? Now keep in mind that if we made this standard normal, that the mean for the set that we're dealing with would be 0, right? So we're really just talking about this is equal to some value, and a lot of times we're going to set maybe in this instance we're like setting it equal to 0.5 or something, right? So the difference between the actual and the ideal values that we're looking for here is 0.5. And then we're just simply saying, well, what else do we do? Well, now we have a way of just plugging in these values here of saying that whatever this value for z is times 1 divided by, in this case, 0.5, right? All that squared will tell us what the sample size needs to be. So when you're doing a study of some sort and you're wanting to determine how many samples do I need to collect to be able to say that my margin of error is below a certain level, and this is what I do, I'd go find my z table, right? I'd do a standard normal here and I'd find whatever this value is, I plug it in there, and I got it. In this case, it'd say 0.05, which is 95, or maybe I want 0.1, which would be corresponding to a 90% confidence interval. And then I'd say, if I want that type of correctness, and that's the word I'll use for right now. I have other videos where we'll lock that down a little bit more. But if I want that level of correctness to my study, this is what my value for n needs to be. And this is the standard formula for that, is this thing right here to allow me to do that. Now, this is something that you'll probably use from time to time if you do statistical work. There are programs out there that will do this stuff for you on multiple levels, right? And then all you have to do is just run through and figure out what sample size you need to use here in order to make everything work. All right? So there's just a little bit of algebra to let you see where this formula comes from. I have another video that we'll post that should be near this one that is going to go through and actually use some of this to actually answer some questions for us. Okay? Hope you enjoyed.